Okay, now let's continue. Now, before I before we discuss this next rule, namely called inclusion exclusion, I will remind you again of how to perform a union on two sets that are not necessarily disjoint. Assume that we have two sets, S1 and S2. Then, if you are asked the cardinality of S1 union S2, this will be equal to the cardinality of S1 plus the cardinality of S2 minus the cardinality of S1 intersection S2. Yeah? Why? Because there is a possibility that they are disjoint. If you add this one and this one, then inside of this one, there is actually S1, yeah, intersection S2. You can see this basically by using a Venn diagram. So yeah, now we can generalize this to three sets. So if you have three disjoint sets, well, if you have three not necessarily disjoint sets, so any set, any uh, any sets but whatsoever, then the cardinality of S1 union S2 union S3 is equal to the cardinality of S1 plus the cardinality of S2 plus the cardinality of S3 minus, look at this, the cardinality of S1 intersection S2 minus the cardinality of S1 intersection S3 minus the cardinality of S2 intersection S3 plus the cardinality of S1 intersection S2 intersection S3 and so on. Yeah. So how do we generalize this into n sets? Well, to generalize this into n sets, I just skip this first to just go to the ninth rule, namely called inclusion exclusion. This is the general case, the union of n sets that are not necessarily disjoint. So that means that in this case, the cardinality of S1 union S2 and so on until Sn is equal to the sum of all cardinality of each element minus the sum of cardinality of the intersection of two sets plus the sum of the cardinality of the intersection of three sets and so on. So what is the pattern here? The pattern here is if the intersection is between even sets, even number of sets, then this is a negative. If it is on all number of sets, it is positive. See? And you can basically generalize this into how many number of sets you have. Okay, let's return to the example. Let's return to the example. And this example is actually quite important for you to understand. So uh, the example is like this. How many permutations? How many permutations of this set 0, 1, 2, 3, 4, 6, 4, 5, and so on until 9 can we find pairs of 4 immediately followed by 2, 0 followed by 4, or look at this, there is an or here, 6 followed by 0. Yeah. So what I mean by this is you have here a set and take any permutation that you like from here. How many permutations are there? You know it already. Number of permutation is basically 10 factorial because there are 10 elements here from 0 to 9. So you take any permutations you like. But those permutations that we are going to take must follow a specific, yeah, must follow a specific pattern, a specific characteristic, namely this one, the first one. Inside of this permutation, 4 must be followed by 2, or 0 must be followed by 4, or 6 must be followed by 0. Yeah, so you have the idea. How many possible permutations are there that basically satisfy this rule? So let me take an example. Uh, Take this permutation 7, 2, 5, 6, 0, 4, 3, 8, 1, 9. This is a permutation of this from 0 to 9. And in this particular permutation, this is a beautiful example. This particular permutation, in this particular permutation, 6 is followed by 0. So this is valid here. But not only that, this is also valid. 0 is followed by, immediately followed by 4. So in this special permutation, here, these two rules are satisfied. So what we want in our original problem is that we want any permutation that satisfies not all of them, one of these rules is enough. So this or this one, this is an or, this is not an and, or this one. So how many are there? So you see, this is actually quite a complicated problem. So how do we deal with this one? Well, we deal with this one by thinking about the rules that we can use and bring this problem to sequence. Our problem here is already sequenced. So right now what we are going to do is just using the rules that we have. Okay, assume P for 2, phi for 2 are the set of all permutation in which 4 followed by 2 appears. So P for 2, phi for 2 is basically all of the permutation, but only when 4 followed by 2. Yeah? So we can also denote P60 and P, so P, not, it is not 60 actually, P60 and P04. These are all defined in a similar way. Yeah? So what do we have to do then? Well, if you know P42, if you know P60 and P04, then you can just take the union of this one. Yeah? And then ask, what is the cardinality of this one? And our problem is solved. But of course, P42, P60, and P04 are not disjoint. So we have to be careful. We cannot use the product rule or the sum rule in the beginning, the summation rule in the beginning, the second rule. We cannot use that. Instead, we have to use this inclusion exclusion rule. That means what we are going to find is the cardinality of P42, because in P42, this contains all permutation that contains 4 followed by 2, union P60, union P04. Yeah? So, how do we determine the cardinality of each of these set? For example, P60. How many elements are there in P60? Think about that. How many elements are there in P60? Well, actually, it is not really difficult. If you think about this, then we have to use the rules that we have seen before. Namely, we are going to find the bijection, and finding the bijection that enables us to solve this easily. How do we do that? Assume 6 followed by 0. You just treat this as one number. Treat this as one particular symbol. Yeah? So that means if it is a symbol, you just put them together, always together, always together. So that means what we are going to find is actually, a permutation of this one. Look at this permutation. All permutation of this one. 1, 2, 3, 4, 5, 7, 8, 9, and 60. Permutation of this one. How many permutation of this one? Well, permutation of this one because how many elements are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 elements right now. It is no longer 10 because you have already fused 6 and 0 together. So there are only 9 elements right now. I mean, how many permutations are there? Easy, because there are only 9 elements there. Then the permutation, the number of permutation is equal to 9 factorial. So that means, according to the bijection rule, the cardinality of phi 60 is equal to 9 factorial. You see? So, and similarly, the same reasoning applies also to P04 and P42. You just fuse them together and then, yeah, they becomes one symbol. And you can find cardinality again. So, what is the idea behind this? The idea is basically when you fuse them together, you basically force them to always fall one by another. Okay. So, we know then P60, P04, P42. But what about the rest? Because here, the cardinality of each one of these is equal to the summation of the cardinality of each one of them minus this one. So we have to cover this one also. Yeah? So how do we deal with that? So the next one is, what about the cardinality of the intersection of two elements, the two sets? For example, P42 intersection P60. Well, we can think about it in the same way. 4, 2 means that I just fuse 4 and 2 together. 6, 0, I will just fuse 6 and 0 together. So how many permutations are there in this intersection? This is just equal to this one. 4, 2, 6, 0, 1, 3, 5, 7, 8, and 9. How many symbols are there left? There are only 8. So that means the number of possible permutation is just 8 factorial. The same reasoning also applies to this one, applies to this one. So each one of them is equal to 8 factorial. Okay? So let's continue. What about the last one? The intersection between these three sets, P04 and then P42 and then P60. Okay, we think about this also in the same way. The bijection must be, if they must be there together, then the only possibility is actually this one. 60 must be followed by 04 and then followed by 42. So that means that you fuse them together. 60 is there, 04 is there, 42 is there. So you fuse them together. When you fuse them together, you know that this must be an intersection that because they are there together at the same time. So they are one symbol. So this is one symbol. The other symbol is 1, 3, 5, 6, 7, 8, and 9. So there are only 7 symbols there. Therefore, the number of permutation is equal to 7 factorial. Therefore, we find this one. So you see, yeah, the number of elements inside of this P42 union P60 union P04 is equal to the number of elements inside of each one of them, namely 9 factorial plus 9 factorial plus 9 factorial minus any two of them, the intersection of these any two of them. The intersection of any two of them is 8 factorial minus 8 factorial minus 8 factorial minus 8 factorial plus the intersection of the three of them, 7 factorial plus 7 factorial. So this is it. Yeah. So this is basically an example of inclusion exclusion rules, and this is the generalization of inclusion exclusion rule. So we can basically right now uh, announce the ninth rule. The ninth rule is inclusion exclusion. Okay, let's let's take another example of inclusion exclusion. This inclusion exclusion is actually quite useful, and there are many possible ways to use this in counting. So how do we compute, how do we calculate the number of primes? We'll use this to calculate number of primes. How many primes are there between 1 until 100? Of course, you can calculate it by yourself. You can take 2 and then 3 and then 5 and so on. You can calculate them. You can count them manually. But we want to basically to use a more sophisticated algorithm. How do we solve this? We will count them by using inclusion exclusion principle. And how do we do this? Instead of counting the number of primes, we'll just count the number of non-primes, or what we call composite. Composites number are the opposite of primes. So if it is not a prime, then it must be a composite problem, a composite number. Okay? Let C be the set of composites, all composites from 1 until 100. 1 is actually a very special number. It is not composite, but it is also not prime. Let's talk about this later. 1 is a special number. It is not a composite number, but it is not also a prime. We want to determine the cardinality of C. So how do we compute the cardinality of C? The cardinality of C, remember, C is a composite. Composite means that it must be a multiplication of something. Yeah, it must be a multiplication of something. So we will divine this one. AM is equal to the element of numbers, a number that is less or equal to 100, x is less or equal to 100, and x is larger than m, and m divides x. Look at this. M divides x. M divides x. So this means that this is the set of all multiplicity of m that is larger than m but not exceeding 100. Let me show you an example. Let's take A2. What is A2? A2 is all numbers less than or equal to 100. X is larger than 2. So that means that 2 is not there. And then M, 2, yeah, 2 divides that particular number. So this is easy. A2 are all multiplicity of 2 and all multiple of 2. What are a multiple of 2? Well, any number that can be, then you can divide by 2. So if it is not included 2, 2 is not included, but it's okay. We start for 4. 4, 6, 8, and so on until 100. Yeah? What about A3, for example? A3 are all multiple of 3, but not 3 itself. Not 3 itself. That means that this is 6. Yeah? This is 9, 12, and so forth. What about A4? A4 is the multiple of 4, multiple of 5, and so forth. You can see that. Okay? Okay, let's continue. Then, our lemma is this one. Our C is equal to A2, union A3, union A5, and union A7. Why is that? Well, this is actually has something to do with the theory of numbers that we have seen before, number theory that we have seen before. We start from A2 because this is a multiple of 2, multiple of 3. What about A4? Why is A4 is not there? Because anyone that is A4 must be inside of A2. Anyone multiple of 4 must be multiple of 2. So you don't deal with that. What about 6? 6 is no longer is not necessary also, because any multiple of 3, any multiple of 6 must be a multiple of 3 also. What about 8? 8, 2. What about 9? 9 is 3, and so forth. Yeah? But why don't we need 11? Why don't we need 11? Well, the second one, this is actually a prime number. 2, 3, 5, 7. The next one is 11. Why don't we need 11? We don't need 11 because 11 is larger. If you multiply that 11 with some number that is larger than 11, then it is no longer less or equal to 100. It's already larger. So we don't need that. Yeah? Okay. So then we know right now that C is equal to A2 union A3 union A5 union A7. The only things left for us to do is to find how many numbers are there inside of these sets. But it is not enough also that, because what? Because a multiple of 2 and a multiple of 3 are not disjoint. For example, 6. 6 is a multiple of 2 and also a multiple of 3. So they are not disjoint. So because they are not disjoint, we have to use inclusion exclusion. Okay? So let's see. For AM here, the cardinality is easy. AM, the cardinality of AM is equal to 100 divided by M minus 1. And you floor this. For example, A2. Why is minus 1 here? Because 2 itself is not there. M itself is not there. So A2, that means that the number of multiple of 2 from 1 until 100. Yeah. How many are there? 100 divided by 2, 50. Why is it minus 1? Because 2 is not there. So you see here, X is larger than M. So M itself is not an element of AM. Yeah. So we know each one of them. So A2 here, how many are there inside of this one? So this one is 100 divided by 2, 50 divided 49. 49 is this one. What about this one? A3. So 100 divided by 3, and then you floor them minus 1 and so on. But they are not disjoint. So what about if they are not disjoint then? So according to the inclusion exclusion principle, this is the element, the cardinality of C is equal to the cardinality of A2 union A3 union A5 union A7, and this is equal to the cardinality of A1 plus the cardinality of A3 plus the cardinality of A5 plus the cardinality of A7 minus the cardinality of the intersection of any two of them plus the cardinality of the intersection of any three of them minus the cardinality of the intersection of any of the four of them. Now, you know this one, you know this one, you know this one, you know this one. What about this one here? This is tricky. This basically says that A1 intersection A3 means that it is a multiple of 2 and a multiple of 3 at the same times. What does it mean? Actually, this is quite easy. This is just a multiple of 6. This is a multiple of 10, multiple of 14, multiple of 15, multiple of 21, multiple of 35. So you know how to deal with them. Yeah? What about this one? This is a multiple of 2 multiplied by 3, 6 multiplied by 5, multiple of 30, and so on. So, yeah? So, so take this one, for example. The cardinality of A2 intersection A3 is the number of elements that is a multiple of 2 multiplied by 3, namely multiple of 6, inside of 1 until 100. How many are there? This is easy. This is equal to 100 divided by 6, and then you floor them. This is equal to 16. Why is there not minus 1? Well, it is not minus 1 because we are 6 itself is there. You don't exclude 6. This is different from this one. A2, for example, here you exclude 2 itself because 2 is a prime, 3 is a prime, 5 is a prime, 7 is a prime. Yeah, but the multiple of 6, 6 is not a prime, so you don't exclude it. So it is still there. And you can right now count them: 49 plus 32 plus 19 plus 13 minus this one plus this one minus this one, and the result is 74. 74 composite between 1 and 100, because there are 70 composites and 1 is special. So how many are there for prime? Well, that means prime will be 100 minus 74 minus 1. This one is for 1. 1 is not a prime, but also is not a composite. So that means that in this example, so that's it. Okay, so let's continue. Uh, in the next topic, we are going to talk about how to count subsets. So what is this? So we may be asked how many subsets are there whose elements are k element that you can take from another set, a larger set that contains n elements. Okay, so what does it mean? Well, originally you have a large set, say that this contains n elements. And right now, how many subsets with k elements that you can take from this set? Yeah, this is important because there are many use of this later on in analysis of algorithm. Yeah, and this question is a fundamental questions in counting and appears in many forms. For example, how many ways are there for someone to select 5 books from 100 books? So, what does it mean? Assume that in my home, I have 100 books. I have a collection of 100 books, and I want to go on vacation and I want to select 5 out of these 100 books. You see, there are a lot of possibility. For example, another way is how many hands, hands is a 13 card in bridge, how many different hands do we have from 52 deck, 52 card decks. So in one deck, and if you are playing a bridge, if you're playing bridge, you have 52 cards because joker is not there, and then you want to create a hand. A hand consists of 13, 13 cards. So how many possible hands are there from 52 cards? Now, these questions arise often again and again. I said it is important for us. And then in the end we have a notation, a specific notation for this one. And this notation is this one. And this one we call this one n select k. Look at that. So how do we read this one? We read this one by n select k. N from n element inside of a set, we select k element. So this one is the, the number, yeah, how many subset of k elements that we can take from a set that contains n elements. So this one is the number of possible ways for us to select k element from n element. Yeah. So this is what we call the subset rule, and this is rule number 10. N select k is equal to n factorial divided by k factorial multiplied by n minus k factorial. Remember that. This is a very important rule. Okay. So let me show you a couple of examples for this one. Okay. Let's see. The first example is called bit sequence. How many sequence of n bits that exactly contains k ones? Hey, if you remember, this is actually our first example. If remember again our donut problem, yeah, how to select a dozen of donuts with 5 flavors, and I have already mentioned before that this is equal to a 16, so it's the number of binary number, 16-bit binary numbers, 16 bits binary number, so n is 16, that exactly contains 4 ones. So if I know how to deal with this problem, then we know right now how to deal with our first problem. Yeah. So how do we deal with this problem? So how many numbers, how many sequence of n bits, how many binary numbers that contains n bits are there that exactly contains k ones? How do we solve this? There is a bijection between the subsets of elements that has n elements to sequence of n bits. How do I create this one? Look at this. How do I create this sequence? For example, this one. Let me show you an example. Yeah. This is a subset that contains 3 elements. Yeah. So you have a set originally of 8 elements, x1, x2, x3, and so forth. Now you just want a subset that only contains 3 elements. How do you create? And these elements are x1, x4, and x5. How do we create this one? Actually, it is not difficult. To create that one, just create a sequence of the elements from x1 until x8, and then you denote it by 1 if it is an element of the subset, f0 if it is not an element of the subset. So x1 here, well, you represent it by 1 in the sequence. x2 is not there, represented by 0. x3 is not there, represented by 0, and so forth. Therefore, according to the bijection rule, then the number of n bits, look at this, n bits, you have n bits. In this example here, we had 8 bits that contains exactly k ones, that contains exactly k ones, in this case 3 ones, is what? This is actually the same as n select k. From n element, you just select k elements. So, yeah. So you see the intuition. So let me repeat again. The number of n bit sequence that contains exactly k ones is equal to n select k, because what you just do is just select k element out of n element. So let us return to our first problem. Our first problem, this is a long way, but I will just go there because we need to go there. This one, yeah. So how many ways are there to select a dozen of donuts with 5 flavors, which I showed you that this is equivalent to this set here, a set of all 16-bit binary string that exactly contains 4 ones. Right now we know how to compute this one. How do you compute this one? This is just equal to n select k. 16 select 4. 16 select 4 is equal to 16 factorial divided by 4 factorial multiplied by 16 minus 4, namely 12 factorial. So you know right now the answer. Okay? So, okay, let me so this is basically what we have just seen, the bit sequence before, and we call this how to compute subsets. Okay, now let's continue with subset division. call this a subset division. Yeah, subset division rule. The rule number 11. Okay, now to select a k-element subset from a set that contains an element, actually, this is what we are just doing here. N select k. Yeah, this is what I mean by n select k. To select a subset that contains k element from a set that contains n element is actually just the same as dividing this set into two subsets. Yeah, namely the first set contains k element and the second one contains n minus k elements. You see the point? Yeah. So if I ask you select k out of n, what you are doing is actually you have one particular set that contains n element and you divide this set into two partitions. The first one contains k element, the second one contains n minus k element. And these problems are just the same. So that means, according to this one, logically, k n select k is just equal to n select n minus k. Yeah? Now, we can generalize this into division to m subsets. How do we do that? Look at this definition. Assume A is a set with n elements and k1, k2 until km are non-negative integers that when you add them together result exactly equal to n. Now we call this division k1, k2 until km of A is a sequence that contains this one. A1, this is a sequence, this is not actually a set. A1, A2, and so on until AM, where AI is a subset of A that is pairwise disjoint, and the number of elements in AI is equal to KI. So what does it mean? It means like something like this. You have A, the number of elements in A is n, and you divide them into m partition. In the first partition, there are k1 elements. The second partition, there are k2 elements, and so forth until the m partition. You have m elements. Here is the first one, the second one, the third one, and so forth until the mth one. The number of elements in A1 is equal to K1, here K2, and so on until Km. You get the idea. Now we can generalize the rule and we call this subset division, the subset division rule. The number of division K1, K2 until Km of a set that contains element is equal to n select K1, K2 until Km. So you see, this is actually just the same as the previous one. The previous one, we just have two, namely K select K1, N select K, yeah? N select K is just equal to N select K1, N select K, comma, N minus K, yeah? So, but right now, if you add this together, they becomes n. And this is equal to n factorial divided by k1 factorial multiplied by k2 factorial and so on until km factorial. Yeah? So, if you have just two division, now here there are m division. If you just have two division, this will be n, k, and the other one will be n minus k. And this is exactly what we have here. N select k is equal to n factorial divided by k factorial multiplied by n minus k factorial. But this one, we can also denote this by n select k, comma, n minus k. See? So they are just a simple generalization. Okay. Now, an example of this one is the bookkeeper rule. So the bookkeeper rule is just the same as this one. I'm not going to explain this in detail to you. The bookkeeper rule, you just read it yourself, but they are just the same because this K1 plus K2 and so on until Km, if you add them together, they will just exactly equal to N here. So this rule and the bookkeeper rule here are just the same actually. So I will just skip this. You can read this yourself. Because I want to go forward to a big example. Yeah. So we don't have much time anymore. I want to go forward to skip to big example, and then we will apply this example to a poker. So let's just continue. We don't have much time anymore. So let me show you a set of examples, and these examples basically demonstrate all of the rules that we have seen before, and we will apply this to a poker game. There are 52 cards in a deck in a poker game, and each of these cards has this value and kind. Okay, so let's continue. So a card has well, in Indonesia we call this down. Down is, I think you call this suit, and this is a rank. The value of the card of the card. Yeah. So this is the suit and the rank. So there are four possible suit. We call this I don't know the name of this one. This is a heart. This is clover. This is a diamond, and this is a what is the other one? I don't know. You can find it yourself. I don't remember the name of that in English. Yeah, and then the rank. Well, there are 13 ranks starting from 2, 3, 4, 5, 6, 7, and so on until Jack, Queen, King, and Ace. So in 5-card draw, so that means you have a poker card 5-card draw. You just draw 5 cards. Every player is given a hand that contains 5 cards. So how many possible hands there are? How many possible hands there are is equal to, well, you have a deck that contains 52 cards, and you select 5 cards from this one. So this is equal to 52 select 5. This is around 2,598,960 possibilities. Okay? Now, let's start from the first one. We call this hand 4 of a kind. What is hand 4 of a kind? When hand 4 of a kind is basically, so kind basically this one, right? We call also this rank. Hand 4 of a kind is basically if you have a hand and this hand consists of one particular suit, and this particular suit has all of them. Yeah, all of 4 of the kind. So for example, this one. Let me show you this example. Yeah, this is a four of a kind. Why is it 4 of a kind? Because you have 8 of this suit, 8 of all of this suit. So this 4 of a kind, and this is the rest basically. This is the 5th card. The 5th card, of course, you don't really know. The second one is also 4 of a kind. Yeah, this is also a 4 of a kind. Now, the problem is, what is the possibility of obtaining a 4 of a kind hand? Yeah, well, we can bring this to our counting problem, and we can map this problem to counting in a sequence. This is not a sequence, but we will be able to bring this into a sequence. A hand 4 of a kind is represented by a sequence that consists of three things. The first one is the rank of this fourth card. For example, in this case, the rank is 8. And then the rank of the additional card, what about this one? The rank is queen. And then you can see this, the suit of the additional one. What about the suit of this one? You don't need the suit of this one because you use all of the suit. Yeah, but for this one you need that. So this is a sequence that consists of three components. So there is a bijection from that. So that means that, look at this. From this one, I create this sequence. And there is a bijection from this one to this one and vice versa. This also, there is a bijection from this one to this one and vice versa. Yeah? So, because of this bijection here, we know how to compute this right now by using the generalized product rule. How do we compute that? Well, take a look at this one. The first one, the kind of the four cards. The kind of the four cards here, well, we have to select one kind out of 13. So that means that there are 13 possibilities. There are 13 possibilities here. What about, yes, this one? The kind of the additional card. Well, the kind of the additional card, because we have already used one kind here, there are only 12 possibilities left. So there are 12 one. Namely, there are 4 possibilities here. So the number of all possibilities are just their multiplication, the generalized product rule, remember that? Then this will be 13 multiplied by 12 multiplied by 4, which is around 624. Look at that. So the number of possible 4 of a kind is just 624 out of 2 million, around 2,600,000. So 4 of a kind is really, really rare. Yeah? So we don't have much time anymore. Please look at the rest of the example. Yeah? Look at the rest of the example. If you have questions, post to me. Yeah? Send me by a message in our WhatsApp group or by email. And I think this is basically the end of our lecture and the end of the course. You will have a final exam, and the final exam basically are from those that I discuss in the lecture, in the last 3 lectures. I will not ask you something that I have not described in the lecture. So the topic that I have covered will be in the exam. You will not be asked questions outside of these topics. So do not worry about that. Do not worry about that. But of course, even though it is like that, I still ask you to read the rest of the book. This is an emergency because we don't have much time because of this virus problem. I still want you to read the rest of the book because discrete math is basically a fundamental course in computer science, and you need to master them to be able to basically master the rest of the course in the program. Okay, I'm really sorry about the time that we don't have. This is basically the end of our lecture today and the end of our course. I hope you will be able to perform in your exam.